So we are going to talk about the second partial derivative test, which allows us to determine whether a function at a critical point has a local minimum, a local maximum, or a saddle point. So to start out, we're going to again look at the single variable version of each of those ideas. If we take a look at a function, say, that looks like this function has three different places where there is a critical point, a place where the first derivative is 0. We have one here at the origin, one here, and one here. The rightmost point on the curve, this point here, is a local minimum. We can see that the function goes from decreasing to increasing, and so around that point, this one here is the smallest value. This second point is a local maximum because it goes from increasing to decreasing, and therefore around this point it is the biggest value. This third point is an example of what we call a saddle point. This function is actually increasing all the way along this region, which means that even though the derivative is 0 here, it doesn't go from increasing to decreasing, and it doesn't go from decreasing to increasing. So this is not an extreme value at all. That's what we call a saddle point. The derivative is 0, and yet it's still not a maximum or a minimum. Now that's pretty rare when we look at single variable functions, but it's actually a lot more common when we jump into 3 dimensions. So we're going to take a look at one example in MATLAB of when that occurs. So the function that we're looking at here is f of xy equals x squared plus y squared plus 8xy. And the reason I've shown this function is because it's a very clear example of what we call a saddle point. We can see two different lines through the curve here. One is this green line, and one is this red line. Both of them pass through this single intersection point, which happens at the origin, and that is a critical value of this function because we see that its slopes are 0 exactly at that point. The problem here is that when we look at the green graph, we see that the function's value is higher around the origin than it is at the origin. As we go along that parabola, the function's value gets bigger than 0. But instead, if we look at going across the red curve, the function's value is less than 0. So what that means is whether the function is going up or down depends on what direction we're moving away from the origin. If we're moving in the direction of the green curve, it's going to get bigger, but if we move in the direction of the red curve, it gets smaller. Because both of those are valid ways to move along our surface, we call this a saddle point. It's not a minimum because this red curve shows that we can get smaller, and it's not a maximum because this green curve shows that we can get bigger. But it's still a critical point, it's just a saddle point. So what we want to do now is take a critical value of a function and determine whether it's a local minimum, a local maximum, or a saddle point. We want some kind of test that allows us to figure that out. So let's start by assuming that our critical value is at 0 because it makes some of the calculations easier and we can use the same ideas to generalize to any point. But if we say our critical point is at the origin, what we're really talking about with a minimum, maximum, and a saddle point is how the function changes when it goes from that critical point to any place in a nearby region. So what we're going to do is take a look at another point that's near that function and figure out how to determine the change in that function from the origin to that second point. And we're going to assume that this change is infinitesimally small so that it makes the calculations a little nicer. Now, in order to find the change in the function from the origin to this second point, which we'll call AB, we're going to try to do this with an integral. And the way we'll do it is by following a particular path from the origin to this point. Because when we follow a particular path, we can think about how the function is changing in terms of its derivatives. And we know how to calculate derivatives very easily. So in this case, we can think about the function f going from the origin to this point here, which is a0, horizontally, and then moving vertically up to the point AB. Now, when we first look at the change in the function along this horizontal segment from the origin to the point a0, we can think about that, the change in the function, as coming from an integral from 0 to a in the horizontal direction? Well, because we're moving in the x direction, what we want to look at is the partial derivative of f with respect to x, dx. By the fundamental theorem of calculus, if we're looking at the derivative with respect to x, and then we integrate it, we'll get back the original function, and then we can find the change between a and 0. So that's our first range of integration. The second range is this vertical segment, which is going to be the integral from 0 to b of f sub y dy, because this time we're moving in the y direction, so we need the partial derivative with respect to y. Now remember at this point that we are looking at a critical value, which means that f sub x at the point 0, 0 is equal to 0, and so is f sub y. But because we're moving from the origin to another point, these derivatives are actually going to end up changing. If we want to find the partial derivative of f with respect to x at a particular point along this range, what we can do is say, let's look at the derivative of f sub x, which is going to be fxx, the second derivative, and integrate that from 0 to the value x. And this is going to be with respect to x again, so we have a double integral, and each one of them is with respect to x. Don't worry if you haven't seen a double integral before. Right now, this double integral is just doing an integral twice, so we don't have to worry about that. For the next part, f sub y, we're going to have to be a little more careful. First of all, we can do the same thing that we did here. The integral from 0 to b of the integral from 0 to whatever value of y we're looking at, of f sub y dy dy. But there's one other thing we have to remember now. When we were looking at the integral going in the horizontal direction, the reason we only needed the second partial with respect to x is because along this range here, y is equal to 0. So if we were looking at a partial derivative like f sub xy, well, this derivative wouldn't matter because y hasn't changed at all, so there's no way for that change in y to affect x if y is staying the same. On the other hand, when we're looking at the region that's going vertically, we actually do see a change in the value of x. X has gone from 0 to a. And therefore, we have to consider one other mixed partial derivative, which is the derivative f sub yx, which is talking about how f sub y changes when x changes. If we assume this is a constant value, we can take the integral from 0 to a of f sub yx with respect to x. This is how much that shift in x from 0 to a has affected the slope in the y direction. That's what our mixed partial is talking about. And then from there, we take the integral of this value from 0 to b with respect to y. Now all we have to do is figure out all of these integrals. And now that we've moved from first derivatives, which we know are 0, to second derivatives, what we're going to do is assume the second derivatives are constants. Because the third derivatives, when we're moving in a very small region, are not going to be able to affect the result that much. We only have to look at the first non-zero order derivative. So in this case, if we do out these integrals, let's see what we get. If we do the first integral in each of these situations, remember that f sub xx we're assuming is a constant. So the integral of a constant is just going to give us x times that constant, f sub xx. And we're evaluating that at the bounds x and 0, so this is the result we're going to get. After that, for our second integral, it's going to be the exact same thing. The integral from 0 to b, this integral is going to evaluate to y times f sub yy dy. And then finally, for our third integral, we have the integral from 0 to b. What is this? The integral from 0 to a of some constant dx? Well, that's going to be a times f sub yx. It's the same situation as we had here. When we integrate a constant over a region, in this case of length a, that's the same as taking that constant and multiplying it by a. Then we take the integral here with respect to y. Now let's see what happens when we do each of these integrals out. This time, f sub xx is still a constant, but x is now a variable. So when we integrate with respect to x, we're going to get 1/2 f sub xx times x squared, evaluated at a and 0. Same thing here, we'll have 1/2 f sub yy times y squared. And finally, right here, not only is f sub yx a constant, a is also a constant. So this is still the integral of a constant. And all we're going to get here is a times f sub yx times y, the variable we're integrating with respect to, evaluated at b and 0. So if we plug these in, remember that 0 squared is 0, 0 squared is 0, and of course 0 is equal to 0. So these lower bounds are all going to cancel out. And what we get as a result is 1/2 f sub xx times a squared plus 1/2 f sub yy times b squared plus a f sub yx times b. So now we have an expression for the amount that our function changes when we go from the origin to the point AB. And it's in terms of those second partial derivatives, so we're definitely making progress. What we need to do now is simplify this expression a little bit so that we can figure out exactly what's going on. Now remember that when we're looking at this change in the function value, we're looking at an infinitesimal displacement between the origin and the point AB. So the idea of length is not really important when we're looking at this situation. What I'm going to do instead is focus on the direction that we're moving from the origin. And one of the ways to define that is in terms of the slope of the line we're looking at. We can think about traveling along this line as being the equation y equals b over a times x. So what we can do in this situation is get this whole equation, rather than being in terms of two variables, a and b, we can turn it down to just one variable, being b over a, by dividing through by the same factor everywhere. So let's see what we can do here. We can factor out 1/2 from everything, and then we can also factor out a factor of a squared. Now let's see what we get as a result. Over here, we already factored out 1/2 a squared, so we'll just have f sub xx. Here we factored out the 1/2. If we multiply by a squared, we're also going to have to divide by a squared. So we'll have f sub yy times b squared over a squared, which we can write as b over a squared. And then finally over here, we took out a 1/2, which means we're going to have to multiply by 2 to cancel that out. And then right here, we have our f sub yx times b, and then a, but we factored out an a squared, so we have to divide by a squared again, which gives us the final result of b over a. That's a over a squared, gives us this a in the denominator. So now that we've found this final expression, we can actually get to the important part of this entire thing that we're doing here, which is we want to figure out whether the change in the function is positive or negative. If we're looking at a local minimum, we know that the function has to be increasing around that point. So this change in the function value should always be greater than 0. Similarly, if it's a maximum, this change should always be less than 0. But if it's a saddle point, then it could be either positive or negative. Now this equation here is a quadratic expression in terms of b over a, which is the slope of our line here that we're allowed to vary however we want. So we want to figure out, if we plug in values of b over a, are we going to get a positive result or a negative result? Because this is a quadratic, we know that it's going to have the shape of a parabola. So there are a couple different options for how this function looks. One is that it's a parabola completely above the origin. In that situation, we know that the change in the function value is always going to be positive. It could be a parabola completely under the origin, in which case the change is always negative, or it could be a parabola like this that is both above and below the x-axis. In this case, there are places where the change is positive and places where the change is negative. So we know this third curve has to be a saddle point. What we want to figure out is how can we decide from this expression which kind of parabola we're looking at. We'll take a look at this. The third curve we drew there has two different roots. It crosses the x-axis here and here. But this first parabola is completely above the x-axis. It has no roots. And the same goes for this other parabola, which means if we use the quadratic formula on these two parabolas, we should get only complex solutions because we don't see any real values that cross the x-axis. And for the saddle point, we should get two different solutions. So let's use the quadratic formula on this equation here, setting it equal to 0, and see what we get for our roots. So if we apply the quadratic formula on this equation here, remembering that we don't have to worry about this term because it's multiplied in everything, so we can just divide it out with a 0 here, we get that the value b over a, that gives us the roots of the equation, is equal to this expression here. And most of this expression is not that important. You can find this expression yourself if you plug in stuff for the quadratic formula, remembering that this is the squared term, and this is the term multiplied by the first power. But what we really want to look at is how do we determine how many solutions there are to this equation? Because that's going to tell us how many roots our function has. Well, look at this square root here. It's called the discriminant. And one of the things that we notice is if this thing inside the square root is negative, we're only going to have complex solutions. We're not going to have any real roots. On the other hand, if what's inside this square root is positive, we're going to have two different roots because of this plus or minus. And therefore, we're going to have a saddle point. So what we really need to focus on is what's inside of this square root. We don't have to worry about the 4 because 4 is multiplied in everything, and 4 times a positive number is still positive, 4 times a negative number is still negative. So what we want to look at is f sub yx squared minus f sub xx, f sub y, y. If we look at this value, if it is greater than 0, then we're going to have two different roots, which means it is a saddle point. And on the other hand, if this is less than 0, then we're going to get a local maximum or a local minimum. So this final statement here is how most textbooks will write the second partial derivative test. Notice that we've flipped around these two values, which means we multiplied it by -1. So before we were saying if this inside expression is greater than 0, we get a saddle. But because we made it negative, now if it's less than 0, we get a saddle point. And if this expression here, f sub xx times f sub yy minus f sub xy squared, is greater than 0, we know we have a local maximum or a local minimum. And we figure out which is which by looking at those second partial derivatives. If, for example, f sub xx is greater than 0, and we know it's a max or a min, then that means it's concave up in at least one direction, so it has to be a minimum. If it's less than 0, then we know we have to have a maximum since it's the other direction. The way that we got here was by starting at the origin with a critical point and looking at how we find the change in value of a function for an infinitesimal change. We can look at that in terms of two integrals of the partial derivatives along these two paths, which we can expand in terms of integrals of the second partial derivatives along those two paths. Remembering that for that second path, because x is not equal to 0, we also have to take into account that mixed partial derivative f sub yx. When we do out that integral, we get this final expression down here, which is a quadratic in terms of b over a. And therefore, we use the quadratic formula to find the roots of places where the change in function value is equal to 0. The reason we care about whether the change in function value can equal 0 is because a quadratic, being a parabola, has to have a few different forms. And we know that if there are two distinct roots, it has to be a saddle point because this parabola can be either positive or negative, which means the change in the function can be either positive or negative. On the other hand, if the thing inside this square root is negative, so we get a complex number, there are no roots, and we know that the change in function has to be strictly above or below 0. And therefore, we're going to get a local maximum or minimum.